All right, let's take a look at our first example problem from Chapter 6. The power generation unit in your plant uses a hot exhaust gas from another process to produce work. The gas enters at 10 bar and 350 degrees C and exits at 1 bar and 40 degrees C. So that's great. I know the temperature and pressure of my inlet and outlet, so my system is fixed or fully specified. The process produces a net amount of work equal to 4,500 joules per mole, and it exchanges an unknown amount of heat with the surroundings. Determine the amount of heat exchanged with the surroundings. Is this heat absorbed or rejected by the system? Calculate the entropy change of the exhaust gas. And then, as a young and ambitious engineer, you seek ways to improve the process. What is the maximum amount of work that you could extract from this system? Assume that the inlet and outlet conditions of the exhaust gas remain the same. We're told that the surroundings could be treated essentially as a bath at a constant temperature 25 degrees C. The exhaust gas could be treated as ideal, and we're given a value of heat capacity. All right, so let me start by drawing a picture, right, so we can try and make clear what exactly it is that we have. Okay, so I have some inlet stream. So presumably some exhaust gas from another process, which is at some known T1 and P1. So initial pressure is 10 bar, initial temperature is 350 degrees C. Okay. Okay. Then it's going to go into some process, right? Some sort of open flow device, and it's going to exit at some temperature T2 and P2, okay, where T2 is 40 degrees C and a pressure is 1 bar. So this is 1 bar and 40 degrees C. Okay. So we know that the process, right, is going to produce a net amount of work equal to 4,500 joules per mole. So this is going to correspond to, so the process produces work. So this is going to be my system performing work on my surroundings. So this will correspond to a work of negative 4,500 joules per mole. Negative because it's work produced, so it's work done by my system on the surroundings. Okay. There's going to be some heat exchange, right? And doesn't tell us if it's heat added to or removed from my system. So I'm just arbitrarily going to draw it as heat removed. When we perform our energy balance, we'll find what the sign of Q is. So now just to be clear, right, this box here, right, this is going to be my device, this open flow device. I'm going to take that to be my system. Right, so it's open, and then I have some inlet stream and I have some exit stream. So it's open, mass can enter and mass can leave my system. So this will correspond to energy balance from Chapter 6 for an open flow system. Okay. So we have everything we were given in the problem statement. So inlet and exit conditions are specified. We have W. We want to calculate Q. All right. So the first thing I'm going to do is I'm going to start by writing my first law balance for an open flow system. All right, so my first law balance is going to take the form of, right, first I have du total dt. So this is my accumulation term. So U total is the total extensive internal energy, has units of energy. T has units of time, right? So this is going to be energy per time. This is my accumulation term. Okay, plus, so if I use the notation from the book, delta, where delta is, in this case, exit minus, or out minus in, or final minus initial. So delta, okay, and then we need to count for difference in kinetic, which I'll write as v squared over 2, plus potential, plus, okay, now instead of internal energy for our open flow device, we're going to write enthalpy, right? So the way I, try and remember this is when I have a flow device, if I think of my, fluid flowing through a pipe, right? If I picture, fluid, moving like a hockey puck, right? So if I were to look at my pipe at some, position down my pipe, and I looked at that, cross-sectional area of the pipe, I'm picturing a hockey puck, say, moving down my pipe. Okay. So as that fluid element moves forward, it has to displace the fluid element in front of it. So it has to perform some PV work in order to displace the fluid element in front of it. Okay, so U plus PV is H, right? So it's H, not U, because of that PV boundary work that essentially needs to be done to displace the fluid element in front of it. Okay, so there's my left-hand side. Now I multiply by m dot. So this is my mass flow rate. Okay, this is going to have units of kilograms per second. Okay, so you could also write in, n dot, a molar flow rate, but here I'm going to use mass flow rate, which is the notation used in the text. And so the idea being is if H, all right, H is my, in this case, specific enthalpy, so energy per mass. Okay, this is mass per second, so H times m dot gives me energy per second, right? So the units match up with du total dt. If this were a molar H, right, then I would have a molar flow rate, or I could convert from one to the other via the molecular weight. All right, and that's going to be equal to, on the right-hand side, similar to our first law of balance, I'm going to write Q dot plus W dot. Okay, the dots just are indicating that this is a rate. So Q dot is going to have units of energy per time. Okay, if you think back to our first law of balance for a closed system, Q and W typically had units of energy per mole or energy per mass. Okay, here I'm going to take it to be Q dot to be energy per time, which agrees with du total dt. Okay, and all right, so I start with my first law of balance for my open system. Next, we're going to simplify. Okay, and so the first simplification I'm going to make is I'm going to assume that my process operates at steady state. Okay, so by operating at steady state, that tells me the du total dt is equal to 0. Our accumulation term is 0. And what it's also going to do for us is our mass flow rate is going to be constant. Right? What goes in is coming out. There's no buildup of mass inside my tank. Okay. All right, so steady state operation, so we'll kill that term. Then the other assumption I'll make, which if I think back to when we first proposed our first law of balance for closed system, right? On our left-hand side, so we think of it as delta U is Q plus W. On the left-hand side, we could include changes in kinetic and potential energy, but what was shown in the book is that those contributions are typically negligible compared to changes in U, right? So we just ignored them, right, and neglected those from our expression. Okay, so we list them here, right, to be included in general. And what I'm going to assume for this process is I'm going to assume that the change in kinetic energy and potential energy are negligible. Right? So I'm going to assume that the change in my kinetic energy and potential energy are negligible. Okay, so that those two terms go away. So what I'm left with then is I'm left with, so I'll write it as delta H. So I'm going to write it as H2 minus H1, right? Delta H times m dot is equal to Q dot plus W dot. Okay, and since we're at steady state, our mass flow rate's constant, I'll divide through by m dot, and what I get is H2 minus H1 is equal to Q dot over m dot plus W dot over m dot. Remember, Q dot and W dot were rates, right? Energy per time. Now we're dividing by mass flow rate, mass per time. So this is going to work out to be just Q plus W, as we had them before, energy per mass. Okay, which agrees with H on the left side. Okay, so my first law of balance reduces to H2 minus H1 is equal to Q plus W. Okay, fantastic. Now let's compute for the problem at hand. So in this problem, all right, we're asked to solve for Q. So solving for Q, I get Q is equal to H2 minus H1, and then it'll be minus W. Okay, cool. So we're told we have an ideal gas. Okay, and so for an ideal gas, H2 minus H1, or delta H, is equal to integral from my initial to final state of Cp dt, and that'll be minus W. So Cp, we're given a value of the constant pressure heat capacity, and it's constant. So that's Cp, ideal gas, T2 minus T1 minus W. Okay, where W was our negative 4,500 kilojoules per mole. All right, so I'm going to jump over to MATLAB here, and let's get things set up to compute. Okay, so let me get Cp. So Cp is 29.3. So 29.3, and this is joules per mole Kelvin. Okay. We're going to need T1 and T2. So T1 is 350 degrees C. I'm going to go ahead and convert it to 273.15 Kelvin. So since I have a difference in temperatures, it doesn't matter if I use Kelvin or degrees C, but I'm going to convert to Kelvin just in case, for the next problem, if I have a ratio of temperatures, making sure that I've got things converted into absolute units and I'm ready to go. So there's T1 and T2. Let me get P1 and P2. I'll keep those in bars. Okay, I won't need them for this problem, but let's just write it down. And I'm going to put a subscript of bar on there to remind myself that it's in bar. So depending on the application, we can convert. Okay, and I'm pretty sure the sinking pressure is 1 bar. Cool. And then W was a negative 4500, and that's joules per mole. It's negative because my system's doing work on the surroundings. All right, so now to compute Q. So Q was equal to Cp times T2 minus T1 minus W. Okay, and so Q will have units of joules per mole. Since Cp is in joules per mole and W is in joules per mole, it'll be joules per mole. Okay, and I was talking in terms of per mass up here, but it doesn't matter. Per mole is perfectly fine. To convert from per mass to per mole, we would just multiply by the molecular weight, and you'd have to multiply the left and right hand side by that same quantity, which would cancel out. Right? So our equation would be the same. We just have to keep track of units. Okay, so there's Q. So let's save this. So it looks like I didn't save this thing correctly. Come on. Okay, so running. All right, I get a negative 4583. So we get Q is negative 4,583. And that's going to be joules per mole. Okay. And since Q is negative, that's going to correspond to rejected heat. The heat's going from our system to our surroundings. So this is going to be heat that's rejected. So in terms of my picture, I got the arrow right, and that this is heat going from my, so rejected from my system to my surroundings. Cool, so it's heat that's rejected. Okay, and I suppose that makes sense, right? My temperature is cooling in addition to the pressure dropping. Okay, so our system's performing work and it's rejecting heat. All right, now B, calculate the entropy change of the exhaust gas. And so I interpret this then as we want to calculate the entropy of my exiting stream minus the entropy of my inlet. All right, S2 minus S1. Okay, so let's do it. So for B, I want to calculate the change in entropy. So I want to calculate S2 minus S1, where we're told we can assume our system's an ideal gas. So that's S2 ideal gas minus S1 ideal gas. All right, now when I look at the problem, okay, temperature is not constant, nor is pressure. So temperature is changing, as is pressure. But no problem, we've got it. Okay. So if I want to calculate a change in entropy, then I go back to chapter 4, and I'm going to start with my definition of entropy. Okay. So namely, I'm going to write that ds, the differential change in my entropy, is equal to T times, and actually I got to get it right, dq reversible, okay, is equal to T ds, right? ds was equal to dq reversible over T. Okay, so here I'm just going to write it as dq reversible is equal to TdS. Now for dq reversible, okay, let's write down our first law balance. So my first law balance is going to be du is equal to dq reversible plus dw, where I'll assume that the only work, right, is reversible PV boundary work. Okay, so dw then becomes negative P dV. Solving for dq reversible, I get the dq reversible then is equal to du plus P dV. All right, so now going back up here then, okay, we have the dq reversible is equal to TdS. And we find now that that's equal to du plus P dV. So ds is equal to 1 over T du plus P over T dV. All right. Got it. So next, okay, in terms of this first term, okay, we're told that we have an ideal gas. Okay. So ds is equal to, well, du is equal to Cv dt. So if Cv dt is equal to u, then 1 over T, so Cv over T dt, plus P over T dV. For an ideal gas, right, my fluid would obey the ideal gas equation of state. So PV is equal to RT. So P over T is equal to R over V, where R is a constant, and V is great because that is my independent variable here. So with that, I get ds is equal to Cv over T dt plus R over V dV. All right, so next we'll integrate from my initial to my final state, my inlet to my exit. And in doing so, okay, so on the left-hand side, this becomes S2 minus S1. So I look at the terms, all right, in the problem statement, we're given a value of Cp. So what's important to remember is for an ideal gas, right? So for an ideal gas, Cp is equal to Cv plus R. All right, so Cv would be Cp minus R. So since Cp is constant, Cv is constant, so I could pull that out of the integral. Then the integral from 1 to 2 of 1 over T dt would be log T2 over T1. Okay, so Cv log T2 over T1. Okay, plus, in the second integral, R is a constant, so I could pull that out. Then I have integral 1 over V dV, so that is log V2 over V1. All right, so I could leave this as is, but we can simplify it some more. So what I'm going to do next is I'm going to use my equation of state again. Okay. So V2 over V1. So I could write that P2 V2 is equal to R T2. and I have P1 V1 is equal to R T1. So dividing, okay, R's would cancel, and I'd be left with V2 over V1 is equal to T2 over T1 times P1 over P2. Whew. So I'm going to plug that in here, and that brings me to S2 minus S1 is equal to CV log T2 over T1 plus R log T2 over T1 times P1 over P2. So I should note, right, we're going to end up with this expression given in the book for the general change in entropy between some initial and some final state. And so you could use that equation. Here I am working through the equation just to hopefully make it clear exactly where all these equations come from. Okay. So equation sheets are good, right? But it's important, even if you have an equation sheet, of knowing where the equations come from and how they're used. So the next thing I'm going to do is I'm going to take advantage of log rules. So let's write this as S2 minus S1. That'll be equal to CV log T2 over T1. Okay, plus, okay, so my argument here, so log of, A times B is equal to log A plus log B. All right, multiplication becomes addition. So this becomes R log T2 over T1 plus R log P1 over P2. So next I can collect terms, right? Common term of log T2 over T1. So CV plus R log T2 over T1 plus R log P1 over P2, where CV plus R is just CP. So I get S2 minus S1 is equal to CP log T2 over T1 plus R log P1 over P2. Phew. And so in the book, this is given as our expression for the general equation for the change in entropy of an ideal gas. Okay, so again, I'm going to emphasize ideal gas, because in integrating the volume-dependent term, we assume we had an ideal gas. This is the equation listed for the general entropy change of an ideal gas between some initial and some final state. If you had an actual fluid, you'd add on, I guess, your difference in residual values, which you could compute using a cubic equation of state. All right, so we have everything. So let's go ahead and let's calculate the change in entropy. So I'll use SI units. So entropy is going to be joules per mole Kelvin. And I'll call this, call it ds of my system. The change in entropy of my system is going to be CP times natural log in MATLAB is log. So T2 over T1. My temperatures here need to make sure they're in absolute units, but we convert it up here when we define them. Okay, I need to define R. So R is 8.314. Okay, and that's joules per mole Kelvin. Okay, so remember R and CP have the same units. So R log P1, so I call it P1 bar divided by P2 bar. Now my pressures, it's okay that they're in bar, not SI units. So all that's important here is that they're absolute pressures. Right? So my ratio of pressures are the same regardless of the units. Right? The conversion factor would cancel. All right. So with that, now I get change in entropy of my system of negative 1.0178 joules per mole Kelvin. Okay, so I'm going to get, I'll call it delta S of my system. It's going to be equal to S2 minus S1. That's negative 1.0178 joules per mole Kelvin. All right, I got Q, I've got delta S of my system. We are cruising along. All right, so now C. As a young engineer, you seek ways to improve the process. What is the maximum amount of work that you could extract from this system? All right, so what we're trying to accomplish in the system is in goes some hot exhaust gas. We extract work, and then exhaust gas is going to come out at some lower temperature and pressure. And so the question is, what's the maximum amount of work that we can extract? So remember, the maximum amount of work that we can extract, or if I think of a process that requires work as an input, the minimum amount of work required is going to happen when Sgen is equal to 0. Okay, so the key is for C. I don't know how I opened up that. The key for C is going to be that my max work will happen when Sgen is equal to 0. Okay, when my entropy generation is 0. All right, so let's write down my equation for Sgen and see where that leads us. Okay, well, Sgen is going to be equal to delta S of my system plus delta S of my surrounding. So now we're told that the inlet and exit conditions of my stream are unchanged, okay, which is great. So delta S of my system, right, I just computed, and that'll be exactly the same. Okay, so delta S of my system, I just computed. I have that. So let's look at delta S of my surroundings. Okay, so delta S of my surroundings, we're told that our surroundings can be treated as a bath. So it'll be delta S of my bath. And delta S of my bath is going to be equal to Q bath divided by T bath. Okay, where Q bath, okay, the amount, say absorbed or rejected by my bath is going to be the opposite of what was absorbed or rejected by my system. So Q bath is just negative Q, where Q is going to be the heat added to or removed from my system. So that's going to be negative Q over T bath. Okay. All right. So T bath I have, or bath was at 25 degrees C. I have delta S of my system. I just computed that. And so what that'll allow me to do then is solve for Q for this idealized case. Okay, so setting this up. So I have delta S of my system is equal to negative delta S of my surroundings, which is going to be equal to delta S of my surroundings is negative Q over T bath. So it'll be a positive Q over T bath. Okay. So therefore, I'm going to get that Q is equal to T bath times delta S of my system. And again, delta S of my system is going to be unchanged from this value because we're told that the conditions of our inlet and outlet streams are the same, right? And delta S of my system is only dependent on, so entropy is a state function, right? So it's only dependent on the conditions of my outlet and inlet. All right, so we can calculate Q. And then once we have Q, well, we can go back to our first law balance for our open system, where we had delta H is equal to Q plus W. Okay, so if we were to resimplify my first law balance for my open system, right, so that was delta H was equal to Q plus W. Solving for W, we get W, and I'm going to call it ideal. So W ideal is equal to delta H minus Q. Okay. And delta H, well, that's going to be exactly as we had in part A, Cp T2 minus T1. And then minus Q, this is going to be a minus T bath times delta system. So let's see what we get. So W ideal, and let's take it in two parts. First, let me compute, and so let me make a note. We'll do these calculations in joules per mole. Let me call it Q ideal. Okay, so Q for this ideal process is, well, first I need a temperature of my bath. So T bath was, pretty sure it was 25 degrees C. So T bath is 25, and again I add to it 273.15 to convert from Celsius to Kelvin. So Q ideal is equal to T bath times ds of my system. Okay, and we know that ds of my system we found to be negative. So Q again will be negative, right, which will agree in terms of sign with our problem from A. Okay, so that's good. Okay, and then once we have Q ideal, W ideal was equal to Cp times T2 minus T1. I'm going to do minus Q ideal since we just computed it. So solving, okay, we get that Q is equal to negative 303.4519. .4519. Okay, and that's going to be joules per mole. And then W, call this W ideal, is equal to, so this is times 10 to the 3, so this is negative 8,000. It's all rated as thousands because the initial value we were given in thousands. Negative 8,779.5. And that's going to be joules per mole. Cool. So I just wrote it twice. So there you have it. Now if we compare to our initial value, so Q is our heat rejected. Before we were rejecting, 4,600 joules per mole. So the heat rejected is a lot smaller, right? The heat rejected is a lot smaller. So before negative 4,600, now it's just negative 303. W ideal. So now it's negative 8,779, and the problem statement was just 4,500. Right? And so what we find is we're producing a lot more work. Right? So more of that energy is converted to work and not lost to heat. Okay, so we produce a lot more work and reject a lot less heat. So produce a lot more work and we reject a lot less heat for that idealized case. Hope that helps. Let me know if you have any questions.